So great. So let's get started. Welcome back, everyone. So we had so almost everyone turned in the homework on time. A few people, I think it's if you haven't turned in yet, it's not quite too late to get credit. You have until the end of the day. You get up to 20% off. So we will, because we grade these with the rubric, to wait till everyone's turned them in to start grading. We'll start doing that. So over the weekend, hopefully get everything graded within the next week or so is the goal. We'll see how that goes. Okay, so let's see, before jumping the schedule, I want to say there's one post. There was a question on Tuesday about whether we could have some office hours in the second half of the week. And so one of the T's, so Hao Sheng, so proposed to move his Zoom office hours. I had set some Zoom office hours up in the evening, and he was the one who said, hey, I'd be glad to move to Thursday from 3 to 5 p.m. So I just, for balance, I would still just keep these regularly on Zoom with this. If there's any strong opinions on this in favor, or so who's strongly in favor of this? And who's strongly opposed to it? Okay, so not as keen to it. So it seems like there's some favor of it, more favor than not. I'll probably try and set up like a poll or something, or a quiz through Canvas to try and grasp the interest. Yeah.
Would the Monday hours still stay?
No, he wouldn't.
Okay.
This would be in place of the Monday hours. Yeah. So there's already a bunch of other things. I tried to spread them out on Monday and Tuesday, but in different time slots. So I know. So I would try doing an evening office hour to see if this would be more helpful. So who's in? Generally would think an evening office hour is kind of an interesting idea. Yeah. So we'll see about that. I guess he was less keen on having the evening office hour. So we'll see if they're the Monday time slot, you'd rather have a Thursday time slot.
Can I see the office hours?
Yeah. Great. Let's look at right. The current office hours. So I have office hours, or I will be available every day after class, Tuesday and Thursday. Mine are Friday morning on Zoom. Maybe I'll move those in person as well. But and then let's see. There's Monday 3 to 5, Monday 7 to 9. These are the ones we would propose to move. And then Tuesday early morning 8 to 10. And Tuesday 2 to 4 p.m. And then homeworks are always due Tuesday night. So there aren't a lot kind of in the second half of the week, especially from the TAs, mainly from me. So it seems people need to think about this a little bit. So I will set up some sort of Canvas way to gather some information on this and get some more feedback. So okay, great. So let's before we jump to changing things, and I know some people had a little confusion. Does in person or Zoom, the days before the assignments are due, I thought we'd have them in person, and there's a Google Calendar to keep track of all of that stuff. So we are starting a new section, and it's may not a new for you if you've had linear algebra before, but I will introduce linear algebra review of this because it will be the language that we use for the rest of the class. And if you're not super familiar with it, you're not going to be able to so follow along with everything we do. So again, we're going to go quickly through basically an entire linear algebra course. This time, basically in 3 lectures instead of 2 lectures, although some stuff you might cover will wind up like eigenvalues and stuff we'll talk about later on in the semester as well. So we're going to so start working on this. Hopefully, even if you, I guess linear algebra was a requirement for this class, hopefully my perspective on it is a bit different. It's how to think about use linear algebra to describe, so data is gonna, how we're gonna think about that. And less on like an ODE perspective of linear algebra, which is sometimes common in how it's taught in the math department. Although that's been changing a bit, so we'll but okay. So we'll go through this fairly quickly, and I'll get to tell you, for instance, today about my favorite mathematical operation. So okay, so the other thing to look out for, homework 2 has been posted. You can find the link either on Canvas or over here. And so the homework 2 you can probably get started on already. The first 2 questions are on the previous 2 sections on the convergence. And then questions 3 and 4 are basically on linear algebra. They're basically mostly asking you to figure out how to calculate stuff and think about these. If you understand linear algebra, it's fresh in your mind. These should not be too hard. Again, question 4 is meant for you to basically try and do inside Python. We will talk about using NumPy in Python in the lecture on Tuesday. It's fairly easy once you kind of learn the basic operations, but this will just force you to work through those sort of things. You could calculate this by hand or MATLAB if you want to, but I suggest you try doing it in Python because we'll be using linear algebra, the NumPy library in Python later on in the class, and so this is your opportunity to use it as a warm-up. Trickiest question, maybe is question 1 this time, maybe 1C, but the rest of them I hope are going to be fairly straightforward on this homework, mostly calculations, applying the stuff you know, making you do the work to learn how to use the stuff we're going over in class. That's the point of homework. It's great. So so you can get started on that, do in a couple of weeks. So okay, let's get to the lecture. Okay, and I will again post something on Canvas about this. So okay, so we are talking about linear algebra, and by linear algebra, I really mean how to think about vectors and matrices, and these are, you could think of them as data structures, as data representations, and they have their own sort of algebra that you can apply on these sort of structures. And this will be kind of the way we describe algorithms within kind of data analysis, because our core representations of data will be as vectors and matrices. Okay, so just to go through this so quickly, we'll often use, say, V as a vector. And what this means is that it has a bunch of values, V1, V2, up to VD. We'll often talk about D-dimensional vectors, okay? And we'll write this as notation that this is a point, this is in RD, okay? This is what this represents. This is, okay, so when I write with these round enclosure, these parentheses separated by these commas. Okay, that means it's in the order that things appear in this kind of this list matters. This is the second, V2 is the second value in the list. Okay, so that's what this kind of notation means. This, like we talked about this, this is saying that it's in the set, and then the set, we're basically, in this language, almost always going to be interested is the real numbers, and it's the real numbers to some power d. Okay, so that means that they're going to be d real numbers. Okay, and and the order of them and the location of them in this order actually matters. Okay, so they're d real numbers, right? So v1 is a real number. It could be, for instance, v1 could be say 7. This could be 3, and if d is equal to 4, then maybe this is 6.3, and this one is 7.8, right? It could be a real, it could be any decimal. It could be kind of, yeah. Typically, okay, so it's going to be these 3 real or these 4 real numbers in this, so in this list, okay, and so there's so typically if you just have a vector, there's some notation, there's some kind of different way of thinking about it where it's written as this kind of with the square brackets, v1, v2, up to vd instead, okay? So this notation indicates that it's a column vector, whereas if I look at what will be the transpose, but I could also represent it as a row vector where I would just do v2 up to vd. Okay, this is the same, meaning the same sort of thing here as each, they're basically all the same thing. These are square brackets. These are kind of parentheses, rounded brackets with commas, okay? And there's sometimes confusion of, is this a column or a row vector? And we'll sometimes have to keep track of this, but mostly not. We mostly, you know, sometimes in equations, you have to be a little bit careful about it. But I often get really confused about, is it a row or column vector? Because really, this is, think of this as a data structure. This is an array, okay? I think all of you have had to take some CS classes, right? And so you think of this, I've allocated an array with some doubles or floats in it. That's what the real numbers means. And it's a length D, okay? And so if I index into the second thing, it's the second entry here, okay? Think of this as a piece of data, and it's got D attributes to it, okay? And so when you, either if it's a column or a row vector, it's still an array. That's still how you're going to store it. So that's why the distinction often doesn't matter. There occasionally, and we'll get in a few places where it is going to matter, but it typically, you don't need to worry about much whether it's a row or a column vector. In fact, Python, sometimes a bit confusingly, sometimes for the best, will always effectively pretend it's a row vector. Okay, it will, and so if you print it out, it will always print it out as a row vector, even if you intend it to be a column vector, right? So Python kind of understands to some extent that it really doesn't matter whether it's a row or column. Okay, so then there's a matrix. Okay, and we'll say a matrix A, and this will be a little bit kind of, we'll say this is going to be an N by D matrix. That will imply that A is going to be an element of R. We'll write N cross D. Okay, so now it's going to be a bunch of real numbers arranged in like so grid. So A is, and we can think about this as let's write it out this way. So I'll try and use uppercase for a matrix and a lowercase value for letter for a vector. And this is going to have a bunch of entries: A11, A12, up to A1D, up to A21, A22, a 2D, so it's going to also N1, and this will be a ND. Okay, and lots of dots in between there. Okay, so what this is saying is that I'm going to have, if I look at each of these rows, I'm going to have n of the rows. Okay, so I'm going to have n rows. Let me write this a little better. N rows, and then if I look at the columns, right, I'm going to have D, so columns here, okay? And so this is a matrix. Again, this can be stored, think of it as either a set of n arrays, each of size D, or it could be D arrays, each of size n. It could be either way. And so, kind of, again, you can store it that way again within, so NumPy, I think it's, the basic thing is n arrays each of size D is how it will basically be stored, an array of arrays, right? And you can index into some object using two indices now, okay? And so I like to think of this as a set of A1 these up to AN, where each of these corresponds with a row. So there are n rows here, and each of the rows now is an element, each AI is an element of RD. Okay, all right, so this is, hopefully you've mostly seen all of this before. What I think is important here is, what I like to think about is trying to think about these in a geometric way. Okay, so where these are powerful is if I think I have, I could think of an array. Let's give an example where A is equal to, let's see, minus 0.5, 1.5, 2.5, 0.75, and 1, 1. Okay, so if I have a matrix that looks like this, this is A. Okay, so if I have this matrix, I can think of it now as these three rows. The first one will be a point, I'll call this A1, and this will be negative 0.5, 1.5. So it's going to be about a point up here. So this will be A1. Okay, A2 be another A2. What? And often we'll think of it as a vector. We can draw a vector from the origin. So this point down here is going to be 0, 0. This is in, again, this is in R2. It's two-dimensional real numbers, right? And so okay, so another distinction in like linear algebra, you often think about column versus row vector. Does that matter? So physics, you often care about whether something is a point or is a vector from the origin. And sometimes that distinction matters so physics, again, that's not going to matter here. For the same object, sometimes we'll treat it as a point, sometimes as a vector from the origin. And we'll use both of those representations. In fact, there'll be an algorithm we'll see later in class where you need to treat the same object, realize that it could be either of these representations. It could either be a vector from the origin or it could be a point. And the algorithm is clever in that it uses the same object to represent either of these. Okay, so so there's this A1 is here. Let's see, A2 is going to be 2.5, and 7.5, that might be out here. This is A2, this vector, and then we're going to have A3 is 1, 1. Let's say this is about here, A3, and this is going to be this vector here, okay? So now I can think of this matrix as actually representing these 3 vectors, and these could be 3, so data points, okay? So these 3 data points here in this space. And a vector is just a way of accumulating these data points into a single representation. Sometimes we'll want to think about them jointly. We'll want to think about the set of the data points and how they affect something kind of on average or something like that. And so then operating on the matrix will allow us kind of some really, we'll use linear algebraic language to kind of compress these operations into kind of some compressed language. And so sometimes some algorithms are actually running a bunch of for loops inside of them, but we can write down the algorithm by just some matrix multiplication or something like that. Okay, so it's important to be familiar and understand this kind of this representation. Can think about these data points, which could be vectors or they could be these points in space, and we can kind of write them in this single object A, which is accumulating all of them in this way. Okay. All right, okay. And then, okay, so I used this notation already on a vector, but a transpose, so a transpose, we'll write it with a little t on the top. And this is basically taking the same data we had before where A1 was a row, and this is turning it into a column, AN, right? So it's just flipping the rows and the columns. And so now a transpose, if I index it, if I take the index ij, the ith row in the jth column, this is going to be equal to regular A, J, I, where I'm flipping these around. Okay. So now if A is in N cross D, then A transpose is in D cross N. Okay, and we did this already with a vector here. I wrote V as a column vector. If I take the transpose, it's a row vector. So when you're dealing with matrices, you kind of need to then be careful about which dimension is representing once, is representing what. N, this is the number of columns. The first value, the second value, typically you do, sorry, hold on, I wrote the wrong thing here. Just seeing if you're paying attention. N is the number of rows, and D is the number of columns. And so when I do A transpose, that flips that relationship. Okay, so I said before, I typically like to think about the rows as being data points, and they live in a, if it's, there are D columns, and they live in a D-dimensional space, but there's no reason we couldn't do it the other way around. And occasionally some subtle ways we'll have to flip this and treat the columns as data points, and they live in an n-dimensional space. Okay, and you can see that because if I do a transpose, well, A transpose is still a matrix, and so it still represents the same thing. You know, it's the same sort of data structure. I've just flipped the role of the rows and the columns. So that means my intuition can flip as well. And so what's sometimes confusing is there's some like algorithms that are studied, and some of the authors will write papers that says, well, assume the data points are the rows in a matrix, and other authors will write, well, assume the columns of a matrix are the data points. And you have to kind of be able to do this transpose kind of in your head sometimes. But I will try and keep it so typically the rows are are what we think of as the data points. But that's not universal across all of the literature in data science. Okay. Just give an example of where this arises and where you can get where these linear algebraic notation is useful. Okay, is when I write out some linear equations, right? So let's say I write 3x1 minus 7x2 plus 2x3 equals minus 2. And I wrote out minus 1 x1 plus 2x2 minus 5 x3 equals 6. Okay, so I've got, in this case, I have two equations and I have three unknowns here. Okay, and so I could have more equations and more unknowns, but these are linear equations in this way, right? I'd like to somehow turn this into a matrix, use a matrix that's going to be in, let's say, that's in a 2 by 3 matrix A. Okay, and if I do this correctly, let's write out A equals 3 minus 7, 2 minus 1, 2 minus 5. And then I can, so I'm going to, this is all the coefficients here, right? I've just mapped them into a matrix. And then I can write, so this corresponds with kind of A is going to correspond with all of these coefficients here. And then I can write out, this is going to be equal to B. This is now going to be a vector, minus 2, 6. Okay. And then I can also write a vector of the variables, x1, x2, x3, and of course we'll call this x. Okay, and then I can put this all in a single simple equation, ax equals b. Okay, so now I've turned, once I've encoded this data, these numbers into a matrix, right, and a vector representation, and this can get bigger and bigger. I can have more than 2 equations, more than 3 coefficients, but if I encode it in the matrix, then I can write the equation as ax equals b. And that encodes all of what's going on here. And we'll break down these operations in a second, but it kind of allows you to encode these more complex sort of things, right? And later on in class, we'll basically see, well, how can you find the best x to try and align with some data? That's what like regression is going to be if you haven't seen that before. Okay, so it allows us to encode a lot of information into a simple equation, and then we can kind of write stuff in terms of this very simple equation, but it will apply to any size matrix and vector as long as the dimensions of everything work out like they're supposed to. Okay. Okay, but to talk about this, you know, I put an A next to an X, right? And maybe you're used to this notation. There's some multiplication going on, and maybe if you want it to be equal to 0, maybe there's some addition, subtraction going on. We need to define these addition and multiplication terms in order for this to work. Okay, so let's go and do this. Okay, so first let's talk about so addition. This addition is fairly easy. It's all addition in linear algebra is so element wise. Okay, well, you can define other things, but we're basically going to work on this this element wise addition is going to be the standard thing. Okay, so I'm going to have, let's say I've got 2 vectors x and y, which are both in RD. Remember, that means x equals x1, x2 up to xd, and y is also y1, y2, up to yd. Okay, then I can write z is equal to x plus y, right? So now I've included a whole vector representation here, and I can just add together the vectors, right? And the result here is going to be another vector z, and the first entry is x1 plus y1, then x2 plus y2, and so on up to xd plus yd, and this is again going to be an rd. This is the same dimension as before. Okay, in order for this to work, one important thing to pay attention to is that in order to add two things, whether they're vectors or the same will be true with matrices, they have to be the same dimension here, right? If x was 3-dimensional and y was 4-dimensional, I can't add them. Okay, I can't do it. It's an undefined operation. Okay, so if you try and do it in a programming language like in Python and NumPy, it's going to throw an error. It's going to say you can't do that. Okay, and it's because I'm adding up the elements here. Okay, there's some places, sometimes in papers, they'll do something like this and they'll implicitly pad something with zeros or something. But basically, the formal way to think about it is they need to be the same dimension, so you can add them because it's an element-wise addition is what's going on here. Okay, again, let's look at the geometry of what's going on here, because I think this is useful to keep in mind. I could think of a vector A. Let's do x and y again. X, and I can think of another vector y, and I want to add these together. I have two vectors now, or two data points. In this case, it's useful to think of them as vectors in this case. And what do? Well, I just kind of chain these together. Okay, so I'll think of this is plus x, but I could also do, and so then this value here will be this will be x plus y up here. So I walked along y in this vector, and then I say, now I'm going to plus x. I'm going to walk along x. And a nice thing is that I could have instead done x and then walked along y, and I got the same answer. Okay? So I can kind of stack these two together, and I can get there in either direction. Okay? So this is kind of a very useful way of thinking about adding together vectors. And because I can add negative numbers, this also defines how subtraction is going to work as well. All right. Okay, and so these are, yeah, so I can flip the order of operations, and I get the same answer. Okay, so if I do addition, let's say I've got A and B in Rn cross D, so they're both the same dimension again. I can do the same thing. I can say C is equal to A plus B, and this is defined, or if I look at the ith and j element, where I is in 1 up to n, and j is in 1 up to d, right? So the ith row and the jth column, then this is equal to aij plus bij, right? It's just element-wise addition. Okay, so just adding is pretty so straightforward. Okay. I don't know, so we can probably, yeah, so the vector adding example is a simple example of doing this as well. But again, it's essential that we have these objects are in the same domain, otherwise I can't add them together. They have to be in the same domain for me to add them the same size. Okay. Okay. We are doing pretty good in time. flying through this, which I think is great. Okay, so let's, I guess, go through a simple example here. 3 minus 7, 2, minus 1, 2, minus 5. I think this was the example from before. And B, let's see, 2, 5, 3, 4, 8, 1. So can I add these two matrices together? Is A plus B a legal operation? Yeah, right. They're both 2 by 3, right? So the example here, I'm going to get 5. That's 3. That's 3 plus 2. Okay. Minus 7 plus 5 is going to be minus 2. 2 plus 3 is 5. Minus 1 and 4 is 3. 2 and 8 is 10. And minus 5 and 1 is minus 4. Okay. So you can also do subtraction. Subtraction makes perfect sense. You can have negative numbers in these. All that is fine. Okay. So addition of vectors and matrices is pretty easy, pretty straightforward. Okay. Okay. So let's do some multiplication. Okay. Okay, so to define multiplication is a little bit trickier now. I don't need the matrices to perfectly align with each other. I have A in, let's say, N times D, and I'll have B is going to be in D times M. Okay, so now what is aligning is the number of columns of A and the number of rows of B. That's what I need to align here in order to multiply them. And that works if I multiply A times B. Okay, so I'll often write multiplication when you put two things next to each other. So with matrices is so like rabbits. If you put them next to each other, they multiply. Okay, so I don't write a symbol in there. Sometimes the symbol, if you write a multiplication symbol in there, sometimes that means element-wise multiplication, which is not the standard thing to do here. Okay, so we just put the two matrices next to each other. That implies multiplication. Okay, and so if we write this out, this is going to give us, yeah, so this will give us a matrix C, okay? And so the properties we're going to have is C is going to be a matrix which is going to be N times M, okay? So I'm now bringing down the number of rows of A and the number of columns of B. It's going to wind up in C, this problem. The part that's the same, the D is going to disappear. That's going to kind of be eaten up in the algorithm. Okay, and there's just kind of from like a rule point of view, there will be a bunch of different types of multiplication we're going to kind of review, and some of them have like some special properties and nice forms to them. But there's really only one rule that you need to understand. It's that Cij can be written as for k equals 1 up to D. Again, this is the same D here. That's the shared term. That's going to be A I K times B K J. Okay, so in order to get this element of this new matrix C, I'm going to sum along the shared column index for A and the row index for B, and I'm going to sum up and add up those terms. Okay, so this is kind of, I think this does not give a lot of intuition of what's going on here. One thing I like to do is to draw these as so rectangles here. Okay, so we'll do A is going to look like this, A, and let's see if I did this correctly. Let's see if there'll be 2 columns and we'll say 5 rows just by the number of little boxes on my screen here. And we'll do B. It's going to have 2, it needs to have 2 rows, right? That needs to, the columns of A needs to align with the rows of B. And this will be 3 of the 3 columns. So this one is going to be 2 by 3, and this is B. Okay. And this is going to give me a matrix C, and C is going to be 5 by 3. This is going to be C, 3 is 5 by 3, okay? Right, so I've taken the row up here and the columns up here, and when I multiply them together, I'm going to get this new shape. Okay, and then let's do a, when I want to look up, let's say, so Python, let's try and stick with Python notation. They index, right, no, I'm trying to say if they start counting at, I'm pretty sure it starts counting at zero, right? Whereas like MATLAB, I grew up doing all my matrix programming in MATLAB, which starts indexing at 1. But Python goes back to indexing at 0, which is probably something you're probably more familiar with, is how most of the rest of programming indexes by 0, right? So this index is at 0. I guess that's not how I did it in the sum. I guess in the sum here I started at 1 here. Okay, so let's stick with that. Typically, mathematically, when you write math, you usually start indexing by 1 up to the D. Otherwise, I have to go 0 to D minus 1, and that just becomes a little bit messier here. Okay, so let's stick with this, but in programming, you'll index by 0 instead. Okay, so let's look at this element here. This is going to be, let's call this will be, actually, that's not a good choice because it's, let's do this element right here. This will be C. Let's use a different highlight here, color. Okay, so now I've got 2 colors. All right. Okay, this will be, so this is the row number 2. If I started counting at 1, row 2 and column 3 in C. Okay, and I want us to figure out where, if I follow this equation, where is this coming from? Okay, so the I is 2, and that's gonna be most, okay, so there are, the I is 2, this 2 corresponds with this I, and that's gonna correspond with, it doesn't affect B at all, it only affects A, and that's the second row of A, right? So that's over here, this row of A, and okay, and then the 3, this only shows up as the J here, and that's the 3rd row of B, or the 3rd column of B. Okay, and so what we notice is that, yeah, this is great. They're both of length 2, right? They're both of length 2, and so I'm going to take, first I'm going to take this first object in these elements. That's going to be A21 when K is 1. This is A21 and B13. E13. I'm going to multiply them together, and then I'm going to do the same with these objects here. I'm going to take these 2 objects and multiply them together. I'm going to add those up, right? And that's going to end up giving me, right? So as I walk along here, my simultaneous for loop, that's going to give me 1 object here, okay? And so basically, every way I can combine together these, the row and the columns, if I pick this row And this column is going to give me this entry point up here, right? Each pair of things that have the same dimension will end up kind of, I'll put those together to be one object inside this matrix C. Okay, and so if I can remember this one definition of how to define Cij, this one thing here, then I can figure out all these versions of matrix multiplies encoded in here. This one I find is kind of, this is the most general form, and it's kind of a lot to kind of memorize if you haven't thought about this before. So let's go and look at some special cases that I think have a lot more intuition and structure. And then typically, once I remember the special cases, I'll realize there's a special version of this, and then I'll be able to recall what is going on here, because I'm like, well, this must somehow generalize these easier to remember special cases. Okay, but if you remember this formula, then you're done with multiplication. As long as you remember kind of orientation and when you have vectors involved, the rows versus columns. Okay, is there a question in the chat?
That's just a comment.
Oh, okay, just more of a comment. All right. So, okay, okay. So what I think is also important is these vector products. Okay. And so this, again, it'll be vectors are special cases of matrices. So this is a special case of the previous rule. And there are two types of vector products we need to worry about. And one is going to be much more common than the other one. This is often called the, so we'll start with the inner, so product. There's going to be an outer product as well. This one's also called the dot product. Okay, and so this is going to take two, so we'll say it takes in two, so column vectors. Okay, so X and Y in RD. Okay, and so I have two column vectors in RD. So a column vector in RD is actually, that means X is actually an element of, well, D is the number of, there's a column vector, D is the number of rows. It's actually a D times 1 matrix, right? And Y is also a D times 1 matrix, right? So Y is RD times 1. Okay, can I multiply these two matrices together? So no, I can't do it. So kind of something's a little amiss here. When I write out this inner product, typically you assume a vector if it's not written otherwise as a column vector, and then this is defined often by X transpose Y. Okay, so I take X and I transpose it. So then it becomes X transpose is 1 by D instead of D by 1. And then that D term is the term that kind of is eaten up by the algorithm. Okay, but this is probably a common notation. There are other notations. Sometimes you do X dot Y. This Y is called the dot product. So I put a dot in between them. This is also sometimes used to represent this. In this notation, I did not transpose X. I just said it's a vector. I don't care what orientation is. I'm doing a dot product between two vectors. The notation I like is like this, where I put these kind of pointy brackets, called like L angle and R angle in Sollatech. It's kind of like a less than greater sign, but it's not quite the same symbol. And this indicates an inner product. I tend to like this notation. This one, if people generalize an inner product, and we'll actually see that later on in class with if we do kernel methods, then you'll often put a subscript down here in the bottom right corner of this to indicate how it is being generalized, where that doesn't necessarily apply to these other two two notations here. So, and this one avoids confusion. The dot might be, well, maybe these are scalars and I'm multiplying them together. I don't quite know if I just see x dot y. It's not clear. That when I have this kind of inner product symbols, then it's kind of pretty clear that these should be something like a vector. So it encodes it, and I don't need to worry about whether they're column or row vectors. And I do a transpose here, right? Because if x and y were given as row vectors, and then I took a transpose of x, well, then that turns out that's going to be an outer product operation. We'll see that in a little bit. So if I didn't really know for sure these were column vectors, this doesn't necessarily tell me what the right thing to do is. Whereas with the first one, so if I use these pointy brackets, it's pretty clear what is going on. Okay. Okay, so I can think of this as, again, I can think of this as, again, a row vector up to xd times a column vector up to y1 up to yd. So I write it in these square bracket notation. Now it is clear that the x, after it's been transposed or whatever, is a row and y is a column. So then it tells me, okay, this is a matrix, multiply, and they're right next to each other. So I'm multiplying them, and I know what to do. But in general, you can just write this as I equals 1 up to d, where I do xi multiplied by yi. Okay, so I'm summing over the elements and I'm adding them up, right? So if I remember, that's what was going on here. I was creating a dot product between this row and this column and A and B, and I got out a value. That's kind of, and I do that for every element of this matrix C. I'm doing that with just these vectors here. Okay, I'm just summing up all the elements, corresponding elements in the vectors, and I take the product of each of them and I add these terms up. This is a dot product. Okay, and this has the nice properties that I can, so if I have a scalar alpha, so this is just a real value, okay, then I have these nice associated distributive and commutative properties. So I can do something where I write alpha x plus y, let's say x, y, z are all in Rd. Okay, so plus z, right? So if I have this operation I want to do, well, I can factor stuff out in nice ways. I can do alpha, I can pull out a scalar value. Okay, I can pull out a scalar value, and I can also pull out the plus symbol as well. So I can do x dot y plus x dot z. So this is kind of like the power of the kind of the linearity of expectation. Remember, I could pull out scalars. I could push the expectation inside the sum. This is, again, it's a linear operation. It's like the linearity of expectation is the same linear in linear algebra. Those are referring to the same sort of things, that I can pull out scalars and I can decompose sums. So I have this nice kind of, I can do these nice tricks, and occasionally we'll simplify equations greatly and give a lot of intuition to what's going on and get sometimes faster algorithms by figuring out how to rearrange these things. And the linear properties, the associated commutative and distributive kind of properties allows us to do this. Let's see. You're good. Okay, awesome. Okay. Okay, so this dot product, this inner product is mentioned. This is my favorite kind of my favorite geometric operator. Okay, so don't tell that to my son Max. So he's the close second, but okay. So I guess I didn't have any girls. I guess I could have called them dot. That would have been kind of cool, but okay. Okay, so I'm going to show you an example of a dot product with the drawing here. I think really illustrates the geometric view of what is being encoded here. So an example, we're going to have two vectors. I'm going to call the first one U, and I'm going to call it that for a reason that will become clear later, if not this lecture, later on in the semester. I'm going to, it's going to be 3/5 and 4/5, and V, right? V is our vector. Let's call this one 2, 1. This one matters exactly what it is, slightly less. Okay, so let's draw these. This is U. This would be 3/5 and 4/5. Let's say this is about here. Let's say this is U. So I can think of this as a vector. And I'm going to go and say, let's look at this line through the origin. This will be kind of nice. Okay, but this is U here. And let's draw V. This would be 2 and 1. Something like this. Okay, this is V here. Okay, I think I did okay job. Okay, this is equal to 2, 1. All right, and so I want to look at what taking the dot product of these two numbers is, or these two vectors is going to give me. And okay, so I want to consider the dot product U V, and this is going to just give me a scalar value. Okay, so it's going to give me a scalar, a single number, right? But it's going to give this nice property where I can, and I can interpret it by drawing some geometry here. Okay, so I'm going to project V onto the closest point onto this line which goes through U. Assume that this light line through U went exactly through there, and I'm going to call this. Just for now, let's call this pi of U of V. And this means the projection of V is the thing I'm operating on, projection onto the line through U. This, we'll go back and see this notation later in class, but just so it's later consistent, it's the point that's the closest point of V onto U. Okay, so this line, and the closest point I know, sometimes you'll see in geometry, is a right angle, right? So there's a right angle here. This is 90 degrees to get to the closest point. Okay? Okay, and this is true, and so I can write turns out the dot product in this case is going to be the length of the projection onto U of V, the length of this vector. So it's going to be, bring out a fresh color for this length from the origin, right? So there's some vector, okay, so there's some vector out to this point from the origin, and the length of this vector is going to be exactly equal to this dot product. Okay. This is only true. I only get this property, and later we'll see. We'll write this as the length, just so this notation is consistent with your notes later. The length can write it as a norm, right? So this is only true when U is going to be a unit vector. So U, this is true if the length of U is exactly equal to 1. Okay, and I chose U so its length is exactly 1. It's kind of simple, non-trivial, like not on one of the axes, but its length is 1, and I can kind of think of that as it's okay, so I can think of that as there's a ball around the origin. of radius 1, and u lies on this circle around the origin. U lies on there, it's of length 1. Then I can think of drawing a line through u, and I project v onto there, and v is, and the dot product of v with u, a unit vector, that's what u stands for. The length of this projection is exactly the dot product of u and v. Okay, so this dot product is actually encoding the length of this projection. Okay, and so this will be a super useful, super powerful thing when we're dealing with high dimensional data. We'll be doing projections, and this picture should keep this in your mind. Even if I'm in high dimensions, I can kind of think about the space that contains these points in it. There's always a two-dimensional space, and I can just operate in this space. And so this picture is going to be valid even as I go up in higher dimensions. Okay, I can actually recover. I can recover this vector, right? So remember, I'm talking about the length here. The length, the dot product gives me a scalar value, just the length, but I might want to get this vector. Turns out I can recover the vector as equal to, I know it's along this line u, so I can recover it as u times this length, right? Which I'll just write this way, which is equal to u times the dot product of u comma v. Okay, so I can recover this point as u times the dot product. Okay, so yeah, so I get the vector too because I already knew the direction it was pointing along, which was encoded by this unit vector u. Okay, so this dot product, which is at the heart of what matrix multiplication is doing too everywhere, is really encoding a projection onto a direction. Okay, and if the length of u is not equal to 1, well then the dot product of v u is going to be equal to the length of, so I can the length of a projection of u v, so I still get this divided by the length of u, right? So if I don't have it, I can basically normalize this and get this out anyways. But kind of this picture is like, will be super important, and we'll come back and we'll see this picture in use when we're doing like things like, so like dimensionality reduction, we're going to be projecting onto here. When we're doing linear classification, we're going to be kind of measuring error based on this difference here, right? This length v to the projection, that difference is going to be equal to this length here is going to be the length v minus projection of u of v onto u, right? So again, this is encoded by this dot product because this element here has a dot product inside, right? So this dot product and this and the association with this projection operator is going to be the foundation of kind of thinking about high dimensional data. Anything unclear about this picture? Hopefully we'll see versions of this again, and but when we see the next, we'll probably be using this inside of some frameworks with some other concepts. So kind of let this sink in your mind a bit now. Okay. All right. Okay. Let's talk about, okay, so I said there's also this, this outer product. This is also a vector multiplication. So this is also x and y in RD, and these are column vectors. Then in this case, the outer product is x, y transpose. Right, so this is now going to be x as this column vector, and now y is the row, y transpose is the row vector here, okay? So with the dot product, I took two vectors and I got a single value. With the outer product, I'm not going to get that, right? This is just an instance of matrix multiplication. But the way I've set it up now, right, this is like X is now in R D cross 1, and Y transpose is in R 1 cross D. Okay, so what is the resulting, what's the dimensions of the resulting output of this outer product going to be? Remember, matrix multiplication, D by 1 and 1 by D. What's the dimensions of it going to be? If X was A and Y was B and I get a matrix C, right? Remember, A and B and I get C equals A, B. Was the dimension of C going to be?
D by D.
D by D, right. Yeah, and in fact, I don't even need, I don't even need this property. I can go back here and say X is in RD, but Y can be in R, let's say M. Okay, so now this guy goes up to M. So this can be M and this term up to M. And now C, this matrix, this would be in R D times M. Okay, so now the output is a matrix here. Okay, and so what I can do with this matrix is it's just every element is the multiplication of the corresponding element. So this is X11 is the first entry of this matrix, and this is going to go down to X. X D Y M. This would be X1 Y M, and this is X D Y1, right? And this would be some XI YJ, right? So there are a bunch of other entries in here. Okay, so but the output of this outer product is turning it from these vectors, blowing it up into a matrix. I get the product of all the individual elements. I don't take any sums here. I'm just taking the element-wise products for all kind of like all the elements of A crossed with every element of every value or entry in X crossed with every entry in Y, and each one of them shows up someplace in this matrix in like the logical location. Okay, so occasionally, much more, this is much less common than the inner product or the dot product. Okay, but this does show up sometimes, and it's just, again, a kind of an instance of this matrix multiplication. Okay, and now I do not need, this is one where I don't need the dimensions to match. Okay, so I guess if you really, really want to multiply and your dimensions don't match, then you can do an outer product. Or with matrices, it's like a Kronecker product, I guess, is the analogy of this. Okay. Let me do one final kind of version of multiplication that I think is useful. Matrix vector multiplication. Okay, and so for this one, I'll typically say, let's say I've got a matrix, which is going to be an Rn times D, and then I'm going to have a vector X in Rd. Okay, and so I'm going to want to get a X. Okay, and I've kind of, maybe I've given away part of the answer, but the answer, A multiplied by X, written in this way, it's going to give a value y. What is the dimension of y going to be? So it's, y is going to be dimension n, right? So x is going to be a column vector that's d by 1, right? So I get n by 1, which is a vector, just an n-dimensional vector. Okay, and so this is another quite common. This showed up in, I guess I did ax equals b in that linear equation I did before, right? So this is also common. So one reason I like to think about this one is that I think it's useful to think about A as a series of rows here, right? And now X is going to be, should think of it as a column vector, okay? And this kind of, I think, if you write out what this is, it's going to get back a column vector Y, and every element of the column vector is going to be a dot product. A d dot x. Okay, and so the way, so this gives me a nice, I like to kind of form a mental picture of what this multiplication is doing. You take the second matrix or vector, and you kind of, and let's first just think about with this vector x, and you give it as a column vector, but to multiply it, you kind of turn it on its side, and then you slide it down the rows, right? So I'm getting x here, which is a column vector, and then I slide it. I start with, I turn it outside, right? So there's this turn. So I kind of turn it sideways, and then I'm taking a dot product with the corresponding row, right? And then the output is a scalar value, right? So this is equal to, the output here is y1, right? So this is equal to y1, y2, up to yn. Oh, okay, who knows is the mistake I wrote up here? I mean, yep.
It should go to A10.
Good, right, very good. Right, so this should go to an down here. There are n rows, right? So y should go to yn. Great, so my dimensions need to line up. Great, very good. Okay, so I kind of, I turn this column sideways, I slide it down, and for every row I do a dot product, and pop, out comes a value. Slide down to the next thing, right? Then I go to the next value here, and then out pops a, out pops this value y2, right? And I keep sliding it down and out popping these dot products. Okay, and so this is kind of I think a useful way to think about what is going on here with this kind of matrix vector multiplication. And so now if I have a matrix instead of the vector x, well then I just have a whole bunch of these column vectors that are lined up next to each other, and each one takes turns sliding down A and doing dot products, and each one outputs a column of the output matrix, right? So I do this with the first column x of B, and I get one column of the output, and I do it again, I get another column of the output, right? So this is kind of a way to think of mechanically how this works, and how this is really a bunch of for loops in multiplying, in doing these things, right? And so the total number of multiplications you're going to do here is like n, if these are all n-dimensional, and n by n matrix by an n by n matrix is like n cubed. Okay. Okay, so it's a bunch of nested for loops, and there are 3 nested for loops going over all the dimensions. Okay, and then there's this ancient line of work. Can you speed up matrix multiplication? And it's like the runtime for n by if all the dimensions are roughly n, is about n to like 2.3. They've kind of sped this up with some tricky things that do something else. But in general, you can think about it with just these for loops. And in most cases, this is actually faster to implement because you can unroll these loops and get this very fast and parallelize it in various ways. Okay, but that's beyond what we're going to talk about. So this covered what, yeah, is there any other stuff in the chat I missed?
That one question might be
Okay.
worthwhile addressing. But
So, okay, yeah, so in this class, we do not denote vectors as bold or arrows. So yes, right, so part of this is because I'm going to be writing stuff on the slides, and I don't really know how to write in bold. This is this notation here for this real numbers. This is called like Blackboard bold notation. So it's got the double line, but I can't really write in bold. So I won't be doing that. And the vectors, you know, my handwriting is not that great that you'll be able to tell it's always a vector. It gets kind of messy, right? I find that you often don't, if you're careful with how you define things, you don't need these bold and vector notations you often see in some papers. And so some papers will use that, and sometimes it's effective to bold all the vectors and matrices. I will try a different convention that I found works fairly well. I will say that, matrices, these are going to be, so capital letters. Okay, this would be like A, B, C. Sometimes I use X, right? So vectors are going to be lowercase, so letters. We saw that with U, V. I'll try really hard to get my U's and, oh, you can't see that. Okay, so my U's and V's looking similar. A, B, X, Y, lowercase x and y, right? So these will all be vectors, and I've stuck with that. And if I need to do a scalar, right? So these are n cross d, these are d, and scalar is just real numbers, right? So then I'll try and use Greek symbols. Actually, alpha is a bad example. Okay, well, we use alpha, but I'll try and use gamma and lambda kind of as these Greek symbols for the scalars. The one exception for this is we're going to use alpha as a vector later of coefficients, but that'll have a special case when we're learning about regression and stuff, and hopefully that will be clear. But we'll mostly stick to this sort of convention, and that I find for what we're doing is enough. The papers where you see notation written with bold and vectors, that's usually when they're really, really complicated formulas and analysis where they need this to help distinguish what's going on because they have so many different variables to keep track of, and they need to use this as a kind of a crutch. I will try pretty hard to keep everything we do with a limited amount of notation as small as possible, and then we shouldn't need that. And I think often that's the case. You can really try and boil down the notation, be as simple as possible, and then you don't need these extra kind of things, these conventions to keep track of everything.
And in some machine learning papers, they'll just use italics for scalars.
Oh yeah, so you could use, so
Really help in this class, but
yeah, again, that doesn't help in this class. I would say something that's even more conventional is if you're writing in LaTeX, every time I'm writing a sentence, I will use the kind of the dollar signs, and this encodes it as a mathematical symbol. And when you're writing it, then it becomes in italics in the text. But now this is a vector, which is in italics, right? So I think this is a more proper way of doing it. think a lot of machine learning papers have really, they don't do notation very well. And I think that's essential to math communication. But I mean, it's a good point. There are a lot of conventions, and I'll stick with one that I tried really hard to get right and consistent and simple in this class. But if you're confused, definitely ask, right? There could be kind of stuff I've missed. So all right, okay, so now we know how to represent data as vectors and matrices and do simple addition and multiplication with them. In the next lecture, we'll start getting into other properties, other sort of common operations like norms and think about linear independence. And we'll need to kind of come back to kind of this picture of a dot product and different kind of like extensions of this analogy and then this other analogy about kind of these points as vectors. This will be useful as we're going to start thinking about higher dimensional space. So we go on, but already we're in d-dimensional vectors. So you're already thinking about high dimensional data. It's been just very simple so far. Okay, but we'll keep building on that and it will become natural by the end of this. Okay, great. So let's stop here.